Welcome everybody to today's webinar, The Art of Screening. I am Jill Browning, your moderator today. I can see that we've still got a few people that are logging into the system right now, so we will give it about another minute or so, and then we will begin shortly. Thanks for your patience. Okay, welcome everybody to our webinar today, The Art of Screening. My name is Jill Browning and I will be your moderator today. Before we get started with our presentation today, I do have just a few housekeeping slides to go over. First of all, hopefully you should be able to hear me speak right now. But I do want to mention there are two different ways of connecting to your audio throughout the presentation today in case one happens to go out. So you can connect through your computer, and if for some reason that does not work, there is a telephone line that you can call into to connect to your audio as well. So either of those options should hopefully work for you. And also, due to the large number of attendees that we have on the presentation today, we have gone ahead and muted your lines. But no worries on that. We do want to make this as interactive as possible. So please feel free to type in any questions that may come to mind throughout the presentation today. We do have a Q&A session set up at the end of the presentation today. So there is a questions panel over to the right-hand side of your control panel. So feel free to type that as they come to mind, and we will try to answer as many questions as possible at the end of today's presentation. I also just want to make a quick note. We are in the midst of a live webinar series for the month of May. On the screen, you should be able to see the different presentations that we have or webinars that we have available. Feel free to go take a look at www.veoliawatertech.com for more information on each of those. We do have some that are available in French as well as in English. And in addition to the live series that we are conducting, we've gone back through our arsenal and published more than 40 on-demand webinars that we've done throughout the last couple years. So those are also available over at www.veoliawatertech.com. So feel free to take a look and register for any of those that may be of interest for you, and feel free to watch those at your convenience. We are making available at the end of today's presentation a PDF participation certificate that will be automatically emailed out to you probably within 24 hours or so of today's webinar. So if that's something of interest for you, please be on the lookout for that. And then finally, we do request that you complete a survey at the end of today's webinar. It should take no more than 30 or 40 seconds of that. We do value your feedback. And in appreciation of that, we are offering a $25 gift card raffle. So all of those people that complete that survey will be entered into a raffle to win a $25 Amazon gift card. Okay. And finally, just one more quick slide before I introduce our speaker today. Veolia Water Technologies. We are a leading company within water treatment. We do focus our efforts in 3 key main areas. Technologies, we offer advanced and robust water treatment technologies. We have a large portfolio of over 350 proprietary technologies that we're able to offer to our clients. In addition to our technologies, we are able to pair those technologies in terms of developing projects for our customers, as well as put multiple technologies together to meet required treatment specifications of the clients. And then lastly, we do offer a very thorough service offering, whether it's during the projects or after. So, okay, so now I'd like to introduce our speakers for today. Jason Boomhour first joined Veolia as part of the instrumentation and equipment team after spending 3 years in the chemical piping sector. He quickly gravitated to the chemical and mechanical equipment product lines and led sales for Veolia's Jean Minier pretreatment equipment in Ontario for 5 years. He is now working as part of the process sales team at Veolia Water Technologies Canadian office, covering all of Veolia's technologies for the municipal sector. And we also have with us today Aurélien Polit. Aurélien is the equipment application and tenders team supervisor based in Veolia's Montreal office. With over 20 years of experience in mechanical engineering, Aurélien has 14 years of experience in the areas of municipal wastewater treatment. Aurélien joined Veolia in 2009 as an application specialist for the pre-treatment division and was appointed supervisor in 2015, where he oversees all equipment selections and tenders for North America. So with that, I would now like to turn it over to Jason. Jason, are you with us?
Yes, I am. All right. Welcome everyone to the Art of Screening. My name is Jason Boomhour, your primary presenter for this presentation. Today we will cover, as a reminder, the objectives for screening. We will then review the different types of screens and how the varying technologies in the market actually perform. Following this up is a segment on technical considerations regarding site and the effects on equipment selection. In addition, we will cover the screen technologies available from Veolia and end with question period. Section 1, screening objectives. Design objectives for screening are to remove inert waste like plastic, glass, metal, hair, rocks, and fibrous material from the treatment process. The greater removal levels of these items will increase the reliability and longevity of downstream treatment equipment and address 3 main concerns. Number 1 is to protect the mechanical equipment. The better level of screening capture rate, the fewer pump clogs, mixer realignments, bearing replacements, clogged membranes, sieves, and nozzles. Number 2, to protect process-intensive technologies. It should be expected that energy consumption can be reduced as pumping, mixing, and aeration would all be more efficient when not fouled with hair, wipes, and fibers. And number 3, reduce operational expenditures. Overall screening is an essential process to ensure the operations team does not spend the majority of their time or their budget maintaining fouled equipment. An objective that is not always considered is the need to prepare for future regulations. As we have seen in the last decade, we are now municipally in an environment where tertiary treatment is nearly a standard. In addition, we are also seeing wastewater facilities enter into a phase of process intensification, where advanced technologies are being deployed in retrofit. These technologies, if they are IFAS, MABR, biological aerated filters, MBR, etc., all require high levels of screen capture. Section 2, screening technologies. There are many screen technologies on the market that all seem so very different. However, we can simply divide them into two main categories to represent the primary way screens restrict flow. On the left in our table, we will see unidirectional screens, which are all bar types, wherein the spacing is represented by a horizontal measurement between two parallel bars. On the right, we see an example of bidirectional screens. These are all the perforated and mesh wire types, wherein the spacing is represented by the perforated hole's diameter. The primary differentiating factor between bar and perforated type screens is the ability to capture debris. The diagram on the left shows a bar type screen. This type performs on one of three axes. Based on the bar screen ability to restrict debris in one direction, we classify this type as unidirectional. The diagram on the right shows a perforated type screen. This type can capture debris on two of three axes. Based on the perforation's ability to restrict debris in two directions, we classify this type as bidirectional. The group of technologies seen here are part of the bar type or unidirectional screening family. This includes the various single rake screens, multi-rake screens, and the step screen. All these screens clean, transport, and discharge screening differently, but share the common trait of parallel bars and the limitation of restricting on one of three axes. A trade-off benefit with bar type screens is low head loss, as the amount of steel and channel physically restricting flow is on the low end. This group of technologies are part of the perforated type or bidirectional screening family. This includes the water intake band screens, combined screw screens, rotary drums, and perforated plate vine screens. All these screens clean, transport, and discharge screening differently, but share the common trait of perforations in their plates, drum, or basket. In contrast to bar type, these screens are heavier and more expensive due to the additional amount of steel required to provide high level of restriction of the influent debris. In the following section, we will review third-party research covering the performance of the various screen types we reviewed previously. The screen evaluations were conducted at the United Kingdom National Screen Evaluation Facility, a third-party research group whom has tested 45 screens from 2000 to 2011. The process flow diagram on display shows the facility's controlled and repeatable test facility. The objective of these studies was to evaluate the screening's capture rate and head loss through a number of screens during both static and dynamic operating modes. The results of performance at both operating modes was combined to provide the screen's average screen capture rate. The test protocol was designed as follows. 12 tests were performed on each screen. 6 were done in static mode. This is when the screen is turned on, it's turned off. So kind of like a low flow event. 6 tests were done in dynamic mode. So when the screen is on or a storm event. To calculate the results, the team measured quantity X introduced into the inlet channel, quantity Y removed by the screen, and quantity Z that was able to bypass the screen and travel downstream. To assign a performance value to the screens, the teams used quantity Y divided by quantity X times 100% to devise a screen capture rate. Here are the results of the study shown in the table. We notice, first off, all bidirectional technologies were evaluated to have a screen capture rate higher than 50%. In contrast, all unidirectional types were rated below 50%. Considering we know bar type capture debris on 1 of 3 axes, and perforated type on 2 of 3 axes, these numbers make sense. Looking a bit deeper, we see the bidirectional technologies with known quick cleaning cycles, tight sealing tolerances, and efficient debris transfer have an average screen capture rate of 70% or higher. In section 4, we will review how screens operate, how operation affects performance, and when a screen's performance is most vital. The screen's performance was evaluated during 2 operation modes. Static mode, so like we know, this is when the screen is off. This happens during the dry weather conditions and low flows. This is when the screen starts blinding due to debris accumulating, and the screen capture rate increases in relation to this blinding. And then we have dynamic mode. This is when the screen is running continuously. This happens during higher flows and storm conditions. The screen is being continuously cleaned. The combination of these 2 tests will represent the actual automatic operation of the screen at different weather conditions. Here we show for visual aid screens in static mode and dynamic mode. Blinding of the screen has increased the capture of inert material, providing good levels of screen capture in static mode. The picture of the screen in dynamic mode is a reminder that when in operation, performance is relegated to that of the spacing size, and actually the spacing is able to restrict. The curves represent the efficiency and function of time for unidirectional and bidirectional technologies. For the unidirectional technologies, we notice slow blinding starting from a low efficiency until it gets to a certain higher efficiency that is relevant to freeboard available and the amount of head loss screen can withstand. Blinding basically reduces the size of the opening, which allows to retain more and more debris. We see a large variation of efficiency. When the screen is in dynamic cleaning mode, the openings are cleared instantaneously to go back to their original size. Efficiency reduces considerably in little time, and that is why the average efficiency of bar type screens is around 30 to 45%. For bidirectional technologies, we can see on the right, efficiency starts at a relatively high percentage, continues to increase gradually with blinding based on the same principle. We see then a slight increase in screen and capture ratio as blinding occurs. When the screen is in cleaning mode, the openings are cleared and efficiency returns to what it was originally. Since there is no large variations, the average efficiency is 70 to 85%. The concept of fine screen has been used by manufacturers of advanced process technologies to call for a certain level of protection for their equipment. The typical spec for these technologies calls for perforated plate at 6 millimeters or less. Arguments are being made to identify fine screens as those with 6 millimeter or less spacing without limitation to the type of screen due to the ability of blinding to increase efficiencies. When manufacturers of advanced process technologies are looking at requirements to offer performance guarantee, we think of these two questions. When are screens needed the most? And does spacing equate to protection? The most likely events to deliver high volumes of debris into a headworks system are first flush events. These events are experienced during the start of rainstorms and snow ice thaws. These are the type of events that deliver high flow rates and essentially clean out sewer system by pushing all the settled debris into the headwork screen. The high loadings rate in these events cause the screen to initiate operation and be in dynamic mode for the majority of the event's worst conditions. When evaluating screens in these events, we must consider the screen's performance to beat its screen capture rating while in dynamic mode. With that in mind, we will always recommend bidirectional technologies to ensure high screen capture rate when protection of process is critical. Our recommendations so far: number one, the process treatment downstream will determine the screen type and opening size. In many facilities like lagoons and conventional activated sludge plants, this will mean a bar type screen is a suitable choice. The screen type, number two, the screen type selected should be based on the efficiencies required when the screen is in dynamic mode at peak flow rate. And number three, it is important to optimize the operating modes depending on the plant hydraulic flow conditions and the screen's technical limitations to withstand water differential, while also considering their cleaning speed. In section 5, I will present on the basic principles and equipment selection and how it is a little more work in selecting equipment for installation in existing sites as retrofit. This slide is a good representation of the thought process in selecting a screen for your application. Ideally, we can select the screen for the process, build a new channel, and optimize hydraulics for the screen. This process is shown as linear, but often the work-through is circular, as each stage may create a need for changes or compromises to be deployed, and is especially prevalent in retrofits. In the following slides, we will discuss the technical limitations and offer some insight into modification or add-ons that can help optimize the installation. There are three primary areas of concern when placing a screen in channel. Number one would be freeboard of 24 inches to allow for the advanced operation of screen modes. So you would want this if you're going to be doing some blinding to increase your efficiencies. You would want some play. Number two, velocity through openings optimized for screen type to ensure screen performance. So bar type and perforated type all have a certain velocity that is ideal for the screen's operation. And number three, approach velocity to prevent settling of debris before it reaches the screen or push through debris at the screen. Starting with hydraulics, We can take a look at the picture and graph. See a non-restricted channel has no issue to move influent and is stable hydraulically, as we can see in the picture. By placing a screen in the channel, we introduce restrictions and we increase head loss. This is now our best case scenario for hydraulics in the channel, but not our starting point to determine if the screen is feasible for the installation. In addition to the restrictions from the clean screen, hydraulics should be based on screens at 50% obstruction, further increasing head loss and reducing freeboard. Introduction of the screen plus blinding now has increased head loss in the channel. To eliminate need for constant operation and potential failure, the appropriate freeboard of 24 inches at 50% obstruction should be considered. Ensuring this will allow operators the ability to increase efficiency of the screen by setting the cleaning cycles based on level differential without worry of flooding the channel. When things don't set up perfectly, we can use various solutions to overcome limitations. These methods are useful, but they're not always able to solve major site constraints. For freeboard, we can curb channel walls for depth, can recess the equipment, or we can widen the channels. For approach velocity, we can use weirs, flumes, and velocity plates downstream to change water levels. Another option is to widen or narrow the channels. And for velocity through the openings, similar techniques as discussed above apply, with more major changes like changing flow rates or selecting different screen type or opening sizes may be required. Section 6, the Jean Mounier line of pretreatment equipment. Veolia offers a full line of products to complete a pretreatment system with one vendor. In addition to screens, we carry a line of debris handling equipment, both single stage and multi-stage washer compactors, screw conveyors, and sluices. The grit removal line is led by advanced systems that have reestablished performance for grit efficiency with Mectan V and the BioMectan. In addition to the standard pretreatment product line, we offer 2 models of combination type systems that provide screening, debris handling, or grit removal in one combined system. Our first screen is the Conflow. Conflow is the original Jean Mounier bar screen and has been around since the 1980s. Decades of experience has proven the screen is durable, it's capable of handling the heaviest types of debris. Personally, I've been on site and seen this screen remove bicycles, strollers, sewer bricks, and even cinder blocks. The big advantage with Conflow is the ability of the screen to knock back large objects from the bar rack. This saves nuisance alarms overnight when debris gets lodged or is too awkward to be removed from channel. Think about something like a tree branch. In addition, with freestanding bars, the screen has built-in overflow. Essentially, we can stagger the bars to mimic a finger weir. These benefits are unique to Conflow and the back clean method of cleaning a bar rack. In comparison to the ComfFlow Classic, the ER is a fairly recent addition coming into the product line early 2000. The product addresses well the need of smaller towns and provide good screening removal for conventional activated sludge plants. With 6mm spacing and multiple rakes, the screen provides operators with a nice combination of coarse and fine screening when operating in static mode. Key features of the ER would be low headroom, low head loss, and 6mm bar spacings. The escalator has been in our product line since the 1990s. In the mid-2000s, we introduced an innovation to the brush system that extended brush life 2 to 3 years and increased efficiency on the equipment. With capacities of up to 100 mgd and a screen capture rate of 79%, the escalator is a reliable technology for most any application in municipal wastewater. Some key points for the escalator are perforated plates with a shelf design for larger solids lift capabilities. We've seen earlier one of the pictures where we were removing windshield washer fluid bottles. With industry-leading tight tolerances and sealing, such as a double width foot brushes, neoprene side seals, and solid pins and bushings in our chain. The advanced cleaning system incorporates self-tensioning cleaning brush and internal spray bar for fats, oils, and grease removal from the plates. The Rotark SB is a versatile unit that sees work in standard municipal installation, along with septic receiving station and vertical installs and manhole. These units provide screening, transfer, and compaction from one unit. Options are available to add a press zone to get up to 40% dry solids at the discharge, additional spray wash to get up to 90% removal of organics, and a continuous bagging system for odor control. These units can be placed in a concrete channel. We can also place them in self-standing stainless steel tanks. The Rotark SD is a choice when addressing downstream processes that require capture rates of 80% or greater at large flows. Typical installations for rotary drums are as pre-treatment to an MBR system, where 3mm or less perforations are required. In addition to the high level of screening removal, the Rotark SD also provides compaction up to 40% dry solids at the discharge, a wash system to provide up to 80% organics removal, and similar to the Rotark SB, a bagging system for odor control improvement. And again, this screen can also be placed in channel or in a self-standing stainless steel tank. For those who are not aware, the Jean Mounier Mectan V and Biomectan are highly advanced vortex grit removal systems. The team has innovated these systems to produce better grit removal on the fine scale of grit particles, increased organic separation, and overcame rigid inlet-outlet configurations to produce a variable angle outlet for optimal installation flexibilities. In addition, both screens and vortex grit systems are sized for peak flow, but as we know with screens, the lower daily average flows allow for increased efficiency. For screens, the lower flows allow for blinding, but with vortex grit, it's about residence time, particles in the tank to settle. So with low flows, efficiency climbs. When the Jean Mounier escalator, for example, is paired with a Mectan V or Biomectan, the headwork system is unmatched by any single vendor for high-level downstream protection at peak and daily average flows. To summarize the presentation, I hope some of the key takeaways will be that the screens are designed for protection, and they should be chosen according to the process that they're going to protect. All screen technologies fall under two types. There are bar types and there are perforated type screens. The bar type screens have the lowest screen capture rate. And the equipment selection needs to address not just hydraulics and velocities, but also, again, the required screen type for the process. And when it comes down to it, Veolia will ensure you have support from the design to the installation portion of your project and beyond. Now we'll enter into the question portion.
All right. Thank you very much for that, Jason. Just want to remind everybody, we did have some questions that came through throughout the presentation, but just a reminder to ask any questions, feel free to type those over in the questions panel. And with that, we will open up the Q&A session and we will try to get through as many of these questions as time allows today. So with that, I will ask the first one. Just confirming that screening is done before grit removal. Can you talk a little bit more about that?
Yeah, I can handle that one for sure. It is best to have your screen before your grit removal system. Essentially, we just want to take out as many things that can clog and be a nuisance. And considering grit systems typically would have some type of extraction for grit, then, you know, having a screen up front will prevent clogging.
And we can assume as well, grit removal system, the range of the size of particles is lower than 300 microns most of the time. So we can assume that the fraction of the particles, the heavier particles that is represented by the grit will go through the screen. And the screen is there ready to, as a first barrier of defense, to remove larger particles that are not grit in the end. So yeah, it's better, it's best to have the screens before the grit removal system.
Great, thanks. Another question that came in is, what % blinding of the screen area is generally allowed in the design under storm flow conditions?
So we always size the screens based on the maximum peak flow. So it's either a storm flow or it's the maximum capacity of the upstream pumps when it's not a gravity sewer influent. So that, assuming that we have done the sizing based on the peak flow, then depending on the type of screen, we will allow for between 30% to 50% blinding in our calculations. And so we always check the screen sizing based on the clean screen, and we double check the calculation at 30% or 50% to check what would be the final freeboard with this blinding. The blinding is used really as a reference to check when the screen will have to start the operation and remove the screenings. And the main criteria is in that case, it's the freeboard. It's the freeboard is the distance between the maximum upstream water level and the operating floor. The idea is to avoid any flooding of the operating floor, obviously. So yeah, the calculation, yeah, between 30 and 50%. Then on site, it's more the monitoring of the head loss across the screen using ultrasonic probes that will start the equipment, since it's not really possible to evaluate in the real channel what's the real blinding of the screen.
Great, thanks. Another question is, what is the maximum approach velocity to be maintained in the screen channel?
Aurelian, I'll let you handle that.
Yeah, there's not really a maximum approach velocity. I mean, usually we would say it's more a minimum approach velocity. Then a minimum would be to avoid settling of particles in the channel. So if the velocity are too low, they are really at low flow, there's a risk for that. So there's ways to avoid that by changing the channel width, for example, or using culverts at the bottom of the channel. In the end, when we size the screen, the approach velocity, where I think in the presentation we stated a range of 1 feet per second. It's a consequence of the sizing of the screen itself. So we are more looking at the velocity through the screen, and then we check the consequence on the channel and the approach velocity upstream, and then we can eventually adapt the channel size based. But the primary criteria we are checking is the velocity through the screen, not the approach velocity.
Great. Another question that came in is, are there any special considerations when selecting a screening unit for lagoon systems?
Jason, do you want to?
I would say not really. I mean, with lagoon systems, I mean, a bar type screen's good there, but we also have some lagoons that, you know, it's not always necessary to have a screen. So essentially, if you have a lagoon where you can use the first lagoon as a trash can, then, you know, you can do that if you want. But typically I would just, you know, address a bar screen for a lagoon application, get out some of the bigger things that might be a pain, some of the volume. And so a bar screen at 6 mils or 1/2 inch is going to should be fine.
Yeah, it might differ depending on what's the type of screenings that could be found in the influent as well. If there's a lot of air stringy materials, and if the lagoon have some aeration, you might want to remove those stringy materials. So I don't think there's a unique answer on that. It's really an evaluation based on the specific application.
Okay, great. It looks like we've got time for maybe 1 or 2 more questions here. Another one that came in here is the debris removal done from the screens automated? And then what is the scheduled screen checks and procedures for this operation?
So yeah, the primary principle of a mechanical screen is to have the debris removed automatically. So depending on the type of screen, the type of technology, there's different ways. Sometimes it's just a scraper, sometimes it's just it falls by gravity. We have screens with a cleaning brush and spray washing systems. So, but I'm like, there's always an automated way to clean the screen once the screens have been removed. What was the second part of the question, Jill?
Yeah, the second part, let me find this again, so I apologize for that. Where was my question? I apologize, I lost the question.
Okay, I'll get it here. What is the scheduled screen checks and procedure for this operation? We recommend weekly visual maintenance on all mechanical equipment, just to check that the operation goes well, there's nothing stuck anywhere. Obviously, the control system has a lot of automated alarms in case of blockages and things like that, but it might take a while before something that creates a blockage, but that might require some additional cleaning. Then
there's some light greasing that needs to be done.
Yeah. As for the procedure for cleaning operation, that's part of our maintenance manual. It depends on the type of screen. That could be detailed depending on which screen you are interested in.
But most of it is actually done from the plant rim operating floor too, which is nice. So your visual inspections, you know, a lot of the time you can go around with the grease gun and take care of that quite quickly.
Great. In the essence of time, we will do one more question, and I apologize if we didn't get to your question today. If we did not answer the question that you asked, we will have somebody follow up directly with you. So with that, how much straight length do you prefer to have in the channel upstream of the screen?
Aurélien, do you have that on top of your head?
It's we would recommend 5 times the width of the channel as a rule of thumb, and then it's obviously adapted to depending on the technology of screen and the overall hydraulic profile and all of that. But the primary rule of thumb would be 5 times the width of the channel.
That was a good
Thank you.
question. What about for grit systems? How much straight length should be going into a grit system?
It's about the same. It's really, the idea is to try to have a laminar flow. It's not always possible, so then we have to adapt and evaluate how many change of directions and things like that we could have upstream. It depends as well on what's the channel configuration downstream. All of that will have an effect on the hydraulic profile and the laminar flow. So there's a maximum. I mean, it's up to 5 times, but if the width of the channel is really wide, it could be way smaller than 5 times. 5 times would be probably for the smaller, small width, like 2 feet, 3 feet, and then there's probably a maximum.
Great, thanks. Well, thank you both for your time today. And I do want to thank everybody that joined us today as well. One question that did come in quite a bit was whether you would receive a copy of today's presentation. I do want to mention that today's presentation was recorded, and you should receive a link to the recording within 24 hours, as well as with that PDF participation certificate. Will be sent in that same email. So with that, that concludes our webinar today. I do ask kindly that you fill out that brief survey, and for those of you that do, you will be entered to win that raffle for the $25 Amazon gift card. So if you are selected for that, we will follow up with you directly as well. So with that, we will conclude today's webinar, and we thank you very much for your time.